Welcome back. Let's talk about asymptotics, right? Or the big three, big O and its cousins, big omega, big theta, right? So when we say asymptotics, what do we mean, right? So, well, you think about the word asymptotic, like asymptotes, right? So if we think about math, what happens when, when n or x or whatever gets large, maybe it approaches something, or, hey, we have some function and it approaches that function, right? As n gets large. Right, so in computer science, it's no different, right? What we often care about is an approximate behavior when we have big data, right? A lot of data, the size of it is n, and n is getting really, really big. If we have tiny amounts of data, we don't really care so much about the runtimes usually, right? But we care is what n gets big here. What we want to know is it going to be linear? Right, like sequential search through an array, right? Is it going to be quadratic, like some sorting algorithms, right? Is it going to be exponential? Oh goodness, that'd be horrible, right? But we care about the sort of the main idea. So why do we care? Well, look at how fast they grow compared to each other. So here we have a graph of for different values of n, so the size of the input, and we're actually just tracking the number of milliseconds that it takes to run. And we can see here that we have a linear algorithm, right? That basically, I mean, the data is so small that it takes very, very little time. If you take that times the log of n, it's also growing pretty slowly here. But you see a quadratic is starting to take off a little bit bigger. And if we have this cubic one, this runtime is shooting off the map. Right, well, this is just zoomed into 100. That's not really that big. Let's zoom out and take a look at bigger values of n. So here we go up to 10,000. Now we can see that our linear one down here and our n log n algorithm right here, so are both doing okay. They're scaling just fine. But look at the quadratic, right? Just taking off, and the cubic even faster. So we get runtime of above a second. By the time we get to, operating on 1,000 elements, what if we're operating on 2,000 elements, right? What's happening to this guy? How long is it going to take to get there? It's going to be pretty slow, right? So we just care about this big behavior. And if I double it or I have it or whatever, it's not going to make a huge difference. It's really the underlying function that's the big deal, right? And here are some very typical functions that we deal with, right? So we just looked at these n log n. N squared and n cubed, right? There are ones that are worse. Yikes. Okay, 2 to the n or n factorial, both really, really big functions here. And there are also ones that are faster, right? So you might have log of n, right? So the runtime of binary search is log of n. You might have some operations that you can do in constant time, right? And occasionally you'll see something that's like the log of n times the log of n, and we write it as the log of n squared, right? And we use a similar syntax to how you do with like the square of the sine of an angle, right? Sine squared. Anyway, so this is a pretty good catalog. You can do lots of stuff. We say right here, when someone asks you a big O question, generally the answer is one of these guys right here. All right. So simple rules. So you probably have some intuition with big O, some experience in the past that basically says that you're just gonna focus on the main runtime, right? So you drop your lower order terms, and you look at your coefficients, and you don't care so much about them, and you take what's left, right? So this first function here is big O of n. All right, this guy we look n squared log n. Oh, that's more than just n squared, so I don't care about that. And certainly those are bigger than n. So I just care about this guy, and I don't really care about the 8 out front here. So I'm just gonna n squared times log n, right? N cubed plus 2 to the n plus, who cares? It's 2 to the n, right? I mean, 2 to the n is huge. And so on, right? So, maybe we have a nested loop that runs an n squared, and then we have a sequential loop and another sequential loop after it, and so on. And again, it's the nested loop that matters, right? So your intuition is pretty good. In our next video, we're going to take a look at actual definitions of big O so that we can be a bit more precise. See you then.